be Monday morning. We did variation last night. So we're going to move on. Before that, give an announcement. I have finished grading the exams. However, I'm still waiting for 2 more exams to be taken, which is why the grades haven't posted yet. As soon as I get those exams and grade those, I'll post the grades on return. Exponential function. This is the next function we look at. For any real number x, exponential function is a function with the form f of x equals a times b to the x, where a is any non-zero real number, b is any positive real number except for 1. A is your initial value. B is your base. Domain is all real numbers. And you have 2 possibilities for the range. Either 0 to infinity if A is positive, negative infinity to 0 if A is negative. This means that b to the x itself is always positive. The y-intercept at 0a and the horizontal asymptote y equals 0. So this is the plot of an exponential function starting at 2. We're going to let it increase by 1. Right, so this is just b to the x. And notice how it behaves as your base increases. The general shape itself stays the same, right? All that's happening is that right portion starts to get steeper. Right, this is for if b is less than 1. Now remember, b also has to be positive. So this would be like 1/2, 1/3, 1/4. All right, so I'm going to go 1/2 to 1/20th, decreasing it. So it starts at 1/2 and goes to 1/20th, increasing the denominator by 1 each time. So again, notice what happens is the base gets smaller. Will let me do that. So I can say the base is increasing this way. So going from 1/20th to 1/2. Let the base increase. And notice how it changes this time. It starts off really steep, right, the left-hand side, and then starts to get shallower. But again, notice that for the most part, it has the same shape. So for all b's less than 1, it's going to maintain the same general shape. What's the only difference between b being greater than 1 so let's just get that to 2. Let's get that to 1/2. So what's the only difference between b being greater than 2, greater than 1, and less than 1? How are they related?
When it's less than 1, as x approaches infinity, y approaches 0. When it's greater, they both approach infinity. Or go to infinity.
That is certainly true. So let's just look at that right now. How are those two graphs related? Let's say it that way. It's a reflection. And specifically, it is a horizontal reflection. Actually, it's about the y-axis. very common application of exponential functions. Is exponential growth or exponential decay. Function that models exponential growth grows by a rate that is proportional to the amount present. For any real number x and any positive real numbers a and b, with b not being equal to 1, exponential growth function has the form, obviously, f of x equals a b to the x, where a is your initial value and b is the growth factor or growth multiplier per unit of x. What does that mean? Specifically that part, because that is the definition of exponential growth. Grows by a rate proportional to the amount present. So something's going to be proportional to p. It's growth. Growth is a rate of change. We'll stick with that. You're not going to understand that notation, because that actually is calculus. Calculus is the study of growth, the study of change. And that is its derivative. So dp dx is the derivative of p with respect to x. Remember from our discussion of proportionalities, sorry, not x. That is what you would get. can't even solve that in calculus. You don't even learn how to solve that equation until differential equations, which is after Calc 3. So really, to truly understand exponential growth models, you have to go up through differential equations. We're just giving you what the model is. Right? Saying you have to take my word for it. A really classic example that is used, let's say, to do a thought experiment. You meet a Nigerian prince. It's the classic scam, but we're going to say this is not a scam. He gives you two choices. He'll give you $1 million up front today, or he'll give you 1 penny today and double it every day for the next 30 days. What option do you take? No, it's my meeting. I'm already in the meeting. Go away.
Was it a double?
Do you know how much you wind up with if you take that option?
Isn't it?
So this is going to give us a table of how much money you'll have after each day. So after 10 days, you only have $10. Oh, that's not looking good. Oh, but now look. Okay, after 18 days, we have about 2,600. After 20 days, we're already up to 10,000. Okay. So first 10 days, $10. Second 10 days, it's an increase of just about $10,000, over $10,000. $10 to the 6th is $1 million. So 10 to the 7th is $10 million. You'll wind up with $10.7 million if you take the doubling option. Clearly the superior option. This is the power of exponential growth. Growth may start off small, but it does eventually blow up. At this point, it took really 20 days to start to see the blow up. If I increase it to 40 days, it's just about 11 billion. just another 10 days. At what, another 3 magnitudes? One of my favorite applications for exponential growth. It's the idea of compound interest. So if we think of just simple interest, it's usually a good starting point. How do you calculate the amount of interest? $1,000, let's say you have, and the interest rate is 1%. How much interest do you gain? $10. How'd you get it? The rate times the amount. That is simple interest. Almost nothing works as simple interest. It's a good way to start. Compound interest is when you gain interest on the interest. So that idea then becomes, okay, so you gain $10, so you now have $1,010. Now another period goes by at 1% interest. How much interest did you gain? What's 1% of the new total? 1,010. What? $10.10 out of it. Right, now you have $1,020.10. Another period goes by at 1% interest. So it's 1% of that new amount. That is compound interest. If we follow that logic, we wind up with the formula A of t equals P times the quantity of 1 plus R over N, all raised to the N times T. A is the account value. T is how much time passes measured in years. P is the starting amount of the account. Principal or present value. R is your annual percentage rate, expressed as a decimal. N is the number of compounding periods in 1 year. Can I? There are several examples of compound interest that occurs in your daily life. You think of one. Does a credit card? See, now I know you're lying. Because I know that not everyone in this room does not have a credit card. Doesn't mean at least one.
I have one. I don't use it though. So
Credit card is calculated as compound interest. It's usually daily. Usually compounds every day. Mortgages, compound interest. Student loans, compound interest. Generally speaking, they work in the reverse direction. Because if you make the minimum payment, it pays off interest that accumulated for that month plus some of the principal. So then the amount of interest you pay the next month would be less because you're actually reducing your principal. Student loans are probably the only one that you would notice interest on top of interest. And that's if you're on one of their payment plans that you reduce your monthly payment. Well, that reduced monthly payment very rarely ever covers all the interest. So now you're paying interest on top of that. You're going to pay off all the interest, so you're actually increasing your principal. And you take out $50,000 for 4 years, paying it for 10 years, but you're on a payment plan. You look at your statement and you realize, oh shit, my principal is now $60,000. It's because you weren't paying off all of your interest every month. Another very common type of compound interest is the one that I work with the most. Investments. Savings accounts. Their interest rates are crap. Bonds. Stock can be modeled as compound interest, even though it's technically not, because it's the stock value that changes. You're not really gaining interest on it. But you can think of it as a compound interest, because if you look at the lifetime of a stock, there is a average annual rate of return. S&P 500 lifetime annual rate of return, I think, is about 11%. So on average, every year, the S&P 500 stocks go up by 11%. So you just take that as your interest rate. There are two bases that are used a lot in mathematics. In fact, you've been working with one of the bases your entire life. What base is it? Place. So what place is that 0? And it can go all the way back to what? When you learn about the places. Kindergarten? I don't think you go up that high, but my point stands. Places that. That's the ones, the unit. What about the 9?
Tens,
8,
hundreds,
7.
tens of thousands, hundreds, millions, tens of millions, hundreds of millions, billions.
Keep going. What do you notice about all of them? Units to tens, how'd you get there? 1 to 10. What's the growth? 10 to 100, what's the growth? 100 to 1,000, what's the growth? It's a constant growth. It's 10x, isn't it? They are all powers of 10. Well, your decimals. To do that, I could decrease it. Maybe I could go 987. That's what, the tenths, hundredths, thousandths, 10,000ths, so on and so forth. Decreasing by 10x. So you're decreasing by a magnitude of 10. All of your decimals are also powers of 10. That's base 10. The decimal system is base 10. That's why it's called decimal, deci for 10. So you've been working with base 10 your entire life. Computers. You get into comp sci and you start to study the workings. It's base 2. Called the binary. Zeros and ones. Although, now computers are getting more advanced, I think we're up to 64-bit operating system. Not to 128 yet. That would be base 64. So operating systems right now are base 64. Which is a power of 2, by the way. All right, another common you see with in the workings of programs is hexadecimal. Base 16. 0 to 9, and then what? A through. What's the 6th letter? F, that's what I thought. And then A through F. It's hexadecimal. Right, or 16-bit. However, believe it or not, 10 is not the most common base used in math. There is another base that occurs way more often in mathematics and applied mathematics. call that the natural base. It is base E. We call E the natural number. There's another name for it. E is irrational. That means there's no formula to identify the nth digit of E. But that doesn't mean it doesn't have a formula. It does. So you take 1 plus 1 over n raised to the nth power, and you let n increase without bound, then that value will tend towards E. So again, you don't really need to worry about that official definition. Approximation for E, 2.718282. Remember, E is irrational, so that 8.2 is not repeating. Just happens to work out that way for this. Every calculator has E on it. When working with calculations involving E, it is highly encouraged that you do not use that approximation. You use the E key on your calculator. This constant is also known as the Euler constant. Named after the Swiss mathematician Leonhard Euler. That's the phonetic Euler. Easiest way to fail a math class. Let's pronounce it that way. If your math instructor is any kind of serious mathematician and you pronounce it that way, you will fail. Instantly. You pronounce it that way to a serious mathematician in a dark alleyway, you'll be lucky to make it out of that dark alley. Yet, oddly enough, familiar with him? Should be. Basically what your high school geometry class was based on. called Euclidean geometry. Oddly enough, his name is Euclid, not Euclid. This allows us to define what's known as the continuous growth function. All real numbers t, positive real numbers a and r. Continuous growth decay is represented a of t equals little a e to the rt. A is the initial value, r is the continuous growth rate per unit of time, and t is the elapsed time. If r is positive, then it's continuous growth. If r is negative, it is continuous decay. This is just a special case of exponential growth and decay. Very common example of exponential decay that occurs, radioactive decay. So radioactive decay is an exponential decay function. So how much radioactive substance is left after a certain amount of time has passed? You generally need to know what that substance's half-life is, what the molecule's half-life is. Even then, that's just a simple explanation. It's really not exponential decay, but that would require the study of quantum mechanics, which we will not get into. Calculate the amount of money present. $1,000 is invested at 5% interest for 7 years. And we're using several compoundings. So we'll start with yearly. So remember, that is the formula. So let's simplify this. Because we know what P is, right? P is 1,000. We know R. What's R? R is the interest rate, written as a decimal. know n, we don't know t. Because it's several. Well, actually, we do know t. In this case. Because for each scenario, it's still 7 years. So in this case, t would be 7. It's the number of years that pass. So the only thing that's going to change is n. Which means I can now write this strictly as a function of n. I think I will. I might actually simplify that. Right as a single denominator. Raised to 7n. That's the function we're working with. So for part A, compounding yearly, what is n? Thousand times 1.05 raised to the 7th power. Right, so this is exponential function, base 1.05. What do you get? What did you say it was? So your value is correct, but semantically you're wrong. What are the units? What are the units? 1,407.10. As I said, your value is right, but semantically it's not right. So that's how much in interest. How much in interest did you earn?
$407.10.
5% interest over 7 years. If it wasn't compound interest, 35% over those 5 years. What's 35% of 1,000? Which is less than the 407.10, right? That is what's known as your effective interest rate, right? So what you do is you determine, assume simple interest. What percentage of 1,000 is 407.10? That would be the effective interest rate over the 5 years. And then you divide that by 5 to determine the effective yearly. Right, it compounds per year. So if you just look at it yearly, it is still 5% effective. But it's definitely not as simple as just 35% of 1,000. In fact, it'd be what? 40.71% would have been the effective over the entire 5, so 7 years rather. What about for part B? We compound quarterly. So what is N? You have 4 compounds in a year. So it's no longer 1.05, it'll be 4.05 divided by 4, all raised. The 7 times 4 is 28. What do you get? How much interest did you gain total? Which is more than the yearly, right? So obviously the more compounds you have, the better, right? What about for part C? We compound monthly. What's N? And 7 times 12. I don't have any multiplication tables. What does that give you? kind of sense? How much more interest was that than compounding quarterly? Like what, an extra $2? 3. It's like $2, $2.05. Something like that. It's like $2. Love this one. Compounds daily. What's N? 365. Yeah, you made a very big assumption, didn't you? He ignored leap years. This is actually very difficult. We would technically have to do multiple functions. 7 years, you're guaranteed. I lied. You're more than likely guaranteed 1 leap year, at least, in those 7 years. Why do I say more than likely? Do you know the rules for leap years?
I just know it's every 4 years.
Every 4 years, unless the year is divisible by 100. 2000 was not a leap year. Oh, yes, it was. 2100 will not be a leap year. Because then the rule is, unless it's divisible by 1000, then it is a leap year. So I say more than likely because this could wind up being where that leap year that would fall between the 7 years is divisible by 100, in which case it wouldn't be a leap year. In which case it would be 365 throughout the entire 7 years. But you could also have 2 leap years in there. If your first year is a leap year, then your 5th year would be a leap year. Could be a leap year. So you have 3 possibilities. No leap years, 1 leap year, or 2 leap years. So which one is it? Well, we're going to go with the simplest one. And we're just going to ignore leap years, because really it's not going to make that big of a difference anyway. So we're just going to approximate it as ignoring leap years. 1 leap year, if there is 1 leap year, you're ignoring 1 day of compounding, which in the grand scheme of thing over 7 years is not that much. 2 leap years, you're ignoring 2 compounds, which again over the course of 7 years, over 2100 days is not that much. So if there's any difference, it's going to be like a penny, maybe 2 penny difference, that's it. So it's insignificant. $365 times 7. You cheated. So I award you 0 points. What does that give you? However, some countries actually use a comma instead of a decimal. I have seen it written this way. But then they obviously don't use commas to separate every vowel, every second and third, because that would just get really confusing. They might actually. I think I have seen something like that. But that would just get really confusing. Thankfully, not one of those countries. So, how much more interest did you earn by compounding daily? No, from the previous one. Yeah, monthly. Not even a buck. Just shy of a buck. It was 99 cents. Depending on how the previous one is rounded. If it's rounded down to, if it stays at 3 cents, then it was just an extra buck. If they rounded it up, 99 cents. So we'll say on average, 99.5 cents. So again, really not that big of a difference. Even if you look at yearly, that's only what, 12 bucks extra interest. Not that big of a difference. Oh, well then let's just let n go to infinity, because that's what continuous means. So it's constantly compounding. So for e, we let n tend to infinity. If we take the compound interest formula above, the a of t, what we will find, and again, I will let you prove this in the calculus class, because that's where you have to prove it, that a of t would tend to p e to the rt. What is 0.05 times 7? That would be how much your account has. $1,000 times e to the 0.35. Oops. And this is where I say do not use the approximation for e. If you look at the calculator I recommend, there's your e key right there. Every calculator will have one that is e to the x. E. $14.19 and 7 cents. which was a whole whopping 4 cents more than daily over 7 years. So honestly, well, yes, the number of compound periods per year dictates how much you get, so obviously the more compounds per year, the better off you are. It's not really the biggest factor. What is the biggest factor? So glad you asked. Time, as this next example is going to show. Calculate the money present. If $7,000 is invested at 10% interest, compounded annually for 4 different periods or 4 different lengths of time. Now, where did these numbers come from? So I didn't just pull them out of a hat. The $7,000 as of tax year 2024 is the maximum allowed contribution to an IRA. Main focus for me is Roth. I love Roth IRAs. 10% is the low estimate for the annual rate of return on average for the S&P. So I'm just going to assume that you're doing what the market does. Spoiler alert, you can easily beat it. I do every year. I've averaged probably 20% a year in returns. And compounded annually is just for simplification. It's easier just to think of it as an annual change instead of compounding multiple times throughout the year. So I will not show each one individually on a calculator. I'm just going to set up a code to create a table for me. is. This is assuming that you do not touch it. So you don't add anything to it every year. 50 years, you're going to have, let's call it $822,000 in the account. Keep in mind, that is if you just do what the market does. Let's say you beat the market. Say you average 15% return a year. Look at that bottom number. That's $7.5 million you expect. Where did I pull 50 from? Assuming that you're 18 years old, average age of a freshman. That's what you're expected to do. You scrounge up $7,000 and you just toss it into an IRA and you don't touch it. By retirement age of 68, at 15%, $7.5 million in retirement. Oh, and if you do it in Roth because you're smart, that's all tax-free. That's what a Roth is. Put in the money after taxes. So you pay taxes on that $7,000, and now all of that growth is tax-free. You don't pay taxes on it when you withdraw it. Let's say you can only do slightly better, 12%. You still have $2 million. Again, expected, right? Because markets do go up and down. With the exception of 2021, I've always gained over 20%. 21, I lost 20%. But that's because the market itself was down. Actually, 63.7. And that's assuming you don't add to it. Just imagine if you add $7,000 every single year from 18 to 68, how much money you would have.
How do you calculate that?
You can't yet do calculus for that.
You know how much it would be?
Off the top of my head. And that's assuming they don't increase it, because it does increase every year. And once you hit 55, your maximum contribution goes up by 1,000. So then from 55 on, it'd be $8,000 a year maximum contribution. 401ks work much the same way. So you work, your job offers a 401k, take advantage of it. First, check if they have a Roth option. If they do that, because then it's tax-free growth. The sooner you start, the better. Well, with IRAs, you can't withdraw from it until retirement anyway, otherwise you pay a penalty. But what when I say don't touch, I mean this is assuming you're not adding anything to it. You want to add a company match, that's even better. Because then they match what you put in up to a certain percent. And that matches free money. It's a shame they don't teach that. Simplify. Alright, so just distribute the exponent through. There are two ways to go from here. Obviously, either way I do it, I'm going to write it all over the same denominator. You could expand out each of those two terms and then subtract. Or you could recognize that as a difference of two squares. Right, so a squared minus b squared. A plus b times a minus b. So that's actually what I'm going to do. Here's our a, here's our b. So what would a plus b be? Well, your negative x, even the negative x's drop out, right? You're left with 2e to the x. Times a minus b. Two e to the minus x. That's where those values come from. What's 2 times 2? E to the x times e to the minus x. Under your laws of exponents. Is e equal to 0? No. Any non-zero number raised to 0 power is what? What'd you say? It's 1, isn't it? So e to the 0 is what? It's 1. This simplifies down to 1. Simplify this expression. By the way, we've already simplified the numerator. It's 4. We did that in the previous problem. So I'm going to expand out the denominator. Actually, I need to do that. No, I'm not going to do that. I'm going to get rid of the negative exponent in the denominator. So factor out an e to the negative x. If you factor out an e to the minus x from e to the x, what do you get? E to the 2x. Make that whole thing get squared. Laws of exponents. The exponent goes onto each term of the product. And remember, negative exponents, you flip the position and make the exponent positive. So e to the negative 2x in the denominator will go up to the numerator as e to the 2x. And there's your fully simplified. And as a general rule of thumb, whenever you simplify your expression, your simplified expression should have no negative exponents. Which is why I got rid of that e to the minus x from the denominator. How do you find zeros of the function? So how would you find the zeros of this function? And then do what? How do you want to proceed? obvious first step. Factor out of what? And you're left with what? X minus 1, right? We know something very important about e minus x. What's the range for e to the minus x? What's the range for e to the minus x? Is 0 included? E to the minus x is never 0. Which means I'm allowed to divide by it. Because it's never 0. Zero divided by a non-zero number is still 0. So this just means that x minus 1 has to be 0. Which means what? So you have a single solution in your solution set. Any questions on the exponential function? Exponential function. Right? All exponential functions have that same general shape, right? Is it 1-to-1? Horizontal line test. Draw a horizontal line. Does it ever intersect the graph more than once? Which means it's 1-to-1. What do we know about 1-to-1 functions? every one-to-one function, well, that's the definition. The specific property of one-to-one functions. Every one-to-one function has an inverse. Exponential function is one-to-one, which means it has an inverse function. That is what we studied Monday. So have a good weekend.